Learning a computer programming language seems easy for the most part, but becomes hard and confusing at certain stages. Understanding the concept of recursion is often such a stage. The simple truth is that if you understand normal function calls, you already understand recursion, and I'll show you how. Before that, I'd like to point out that recursion is supported in most programming languages, and in this video, I'm not going to assume any specific programming language. I'm sure you'll be able to follow this irrespective of the language you use. When a function calls another function to get something done, it is often not difficult to understand what's going on. But when a function calls itself, it is sometimes confusing to beginners. Let's look at a standard example for a recursive function to calculate the factorial of a number. Incidentally, recursion is perhaps not the best way to compute factorials, but it's a good illustration. The factorial of a positive number is the product of all the numbers from 1 up to and including the number. For example, the factorial of 4 is 1 times 2 times 3 times 4, and the factorial of 5 is 1 times 2 times 3 times 4 times 5, or alternately, it is 5 times the factorial of 4. Our function uses this idea to recursively calculate the factorial. All recursive functions must have a base case that works without a recursive call. Otherwise, if each call to the function resulted in a recursive call, then such a function would never terminate. Typically, a recursive function calls itself with a smaller value of the input than it was called with. When the input is really small, then the solution is usually trivial, and this is what the base case handles. In our example, we have chosen the base case to be when the input is 1. We should have chosen 0, but I chose 1 for convenience. Since each successive call reduces n by 1, eventually it'll hit the base case and the recursion will stop. Let us go under the hood and see how it all works. Consider a call to factorial 3. This starts an instance of the function. Since n is not 1, execution reaches the line return n times factorial n minus 1, and hence a recursive call occurs to factorial 2. Note that this is a completely different instance of the factorial function. Its variable n, although having the same name as the previous instance, is completely different. At this point, there are two active instances of the function, with each having its own copy of the variable n. In the current instance, n is not 1, and hence a recursive call occurs to factorial 1, which now opens up a third instance of the same function, again with its own copy of the variable n. In this last instance, the base case is reached because n is 1, and the function returns 1 to its caller. And of course, this instance ends. This now enables the second instance to compute 2 times 1 and return 2 to its caller, which finally enables the original instance to return 3 times 2 to the original caller. Notice how the whole process was no different than any normal function call. The fact that each of the functions called was the same function played no special role at all. The only thing you need to watch out for in recursion is that there must be at least one case where the function is not recursively called, the so-called bottoming out case. You will be surprised to see that there are many computations which we do not think normally of as recursive, but which can actually be coded very easily using recursion. There are programming languages like Lisp and Scheme that make extremely good use of recursion and require programmers to think recursively. We hope you found this video useful and look forward to your feedback.